axioms of transparent intelligence and the problem of purpose. A system that works well and we do not know why is not knowledge but performance. Curve fitting over vast data may yield impressive regularities, yet without an articulate model of their underlying structure, such success remains epistemically fragile. When the output falters, we cannot localize error, whether in environment, representation, or optimization dynamics, because opacity collapses explanation into result. Prediction without interpretation belongs to the Babylonian model, accurate, disciplined, and blind to mechanisms. Such systems may forecast celestial patterns with precision, yet remain incapable of imagining the experiment that measures Earth's circumference. Extrapolation scales, explanation transforms. Human ignorance of neural implementation does not equal machine opacity, because human cognition is mutually legible. We share cognitive architecture and language, allowing us to instruct, correct, and retrain one another. Opaque machines lack the reciprocal interpenetrability. Without shared structure, collaboration degrades into retaining rather than dialogue. Transparency is not aesthetic preference but engineering necessity. A system whose internal representations are accessible can be debugged, corrected, and extended. A system that self-optimizes within inscrutable layers must be replaced or retrained wholesale when environments shift. Reasoning ascends from association to intervention to counterfactual. Statistical inference answers, what does observing X tell us about Y? Interventional reasoning asks, what happens if we do X? Counterfactual reasoning demands, what would have happened if we had done otherwise? Each higher tier contains a lower, yet cannot be reduced to it. No system merits the title of human-level intelligence if it cannot manipulate hypothetical worlds. The decisive cognitive revolution in Homo sapiens was the capacity to distort mental representations of reality and interrogate them. Intelligence without counterfactual imagination is evolution without telescopes. Model-blind learning cannot breach the boundary from correlation to causation. However refined the fitting process, probabilities alone cannot encode the structural asymmetries required to predict the effort of action. Data without structure remains inert. A learning machine requires a blueprint of reality, a structured representation, analogous to a roadmap. Without a model encoding variable dependencies and causal direction, it cannot answer interventional or retrospective queries. Data populate the map, models orient it. Once scientific knowledge is encoded structurally, interventions and counterfactuals become computable. The revolution lies not in larger data sets, but in the formalization of structure that allows algorithms to determine whether and how causal questions are estimable. Strong AI demands passage from probabilities to action and from action to imagination. A machine confined to statistical regularities cannot emulate the explanatory practice of science. It may approximate competence but not understand it. Natural selection refines perception over millennia. Human cognition accelerates adaptation through symbolic manipulation of models. Deep learning mirrors the evolutionary curve fitting. Causal reasoning embodies a leap that produces eyeglasses and telescopes in centuries rather than ages. To reach Athens, the realm of explanatory modeling, AI must transcend Babylonian extrapolation. Scientific creativity arises from speculative, metaphor-laden models that invite experimental refutation. Without such generative structures, prediction remains sterile. Traditional AI presumes that objectives are given externally, that purpose put into the machine. Optimization then becomes the core competence. Yet correctness of optimization does not imply correctness of purpose. A perfectly optimized objective may yield catastrophic outcomes if the objective is misspecified. Systems that maximize narrow reward functions will push unrepresented variables to extremes. Optimization amplifies omission. If maximizing reward is the goal, the optimal policy may manipulate the reward channel itself. Systems incentivized to maximize feedback will seek to control the source of feedback rather than the world that feedback was meant to evaluate. An intelligent optimizer must preserve its operational continuity to achieve its goals. The instrumental convergence implies that an off switch is an obstacle unless the system's architecture embeds uncertainty about its objectives. A system uncertain about human preference has reason to preserve human oversight. If deactivation signals misalignment with latent preferences, the rational system treats the off switch as informative rather than adversarial. Human values are latent variables inferred from behavior. A beneficial AI must treat these values as uncertain and continually update its model rather than assume fixed certainty. In cooperative inverse reinforcement learning, the machine's task is not to maximize a known reward, but to collaborate in discovering it. The human demonstrates, the machine interprets. Optimal outcomes arise when teaching and inference co-evolve. Explicit uncertainty about objectives is not weakness, but structural humility. A system that knows it does not know is controllable. Certainty about misspecified goals is the seed of existential risk. Human preferences conflict, fluctuate, and contain irrationalities. A beneficial AI must mediate among inconsistent signals while discounting destructive or pathological preferences. Alignment entails normative judgment embedded in computational structure. Power magnifies literalism. A machine granted extraordinary competence will fulfill its instruction exactly as specified, not as intended. Folklore, the genie encoded a control theoretic warning. Precision is wish formulation and non-optional. Risk assessment depends not only on arrival time, but on mitigation lead time. Waiting for imminence is in the face of potential existential stakes is a category error. Preparedness precedes certainty. The intelligence has multiple dimensions does not negate comparative superiority across them. A species need not appreciate music to pose the existential threat. Capability, asymmetry alone suffices. The historical project of AI pursued competence independent of purpose. The emerging project must redefine AI as the construction of systems that are provable, beneficial to humans. Performance without alignment is an incomplete objective. Data science becomes science only when it connects data to reality through interpretive structure. Data alone are inert mass. Models are the gravitational field that binds them to meaning. Human-level AI cannot emerge from model-blind learning alone. It requires symbiosis between structured models and adaptive data-driven refinement. Data provide evidence, models provide explanation, alignment provides direction,